to use for today. Okay, can everyone see the textbook, chapter 17 pages? Just to make sure everyone can see it. Is my share screen okay? Thumbs up if you can see. Alright, good. Okay, so just let me carry on from here. Now, just a recap not a recap, but just a reminder that remember these lectures are meant to help you understand the key concepts in the chapters itself. It's not meant to help you to after this whole session you're able to do every single question, but sort of like you become clearer in understanding what is this whole chapter about. Okay, there are practices, you have to do it on your own back end. Okay, either use your 10-year series or go through your worksheets that's been given. Okay, so that's the main idea really is to understand the key concepts here. So I'll be running through the pages in the textbook so that at least you understand what is highlighted here, what are important. Practical electricity. Okay, first up, okay, uses of electricity. Every time I'll go through this learning outcome here, just to make sure that you understand what you're supposed to pick up from this particular section. Okay, so in 17.1, the key idea here is that you need to understand how electricity is actually converted to thermal energy. So key idea here is electrical energy, okay, is converted to other forms of energy. Okay, and because electrical energy is converted to other forms of energy, we can make full use of the electrical energy. So electrical to thermal, okay, so what are the things that we make use of it? So we got electric kettle to heat up water, electric radiator to heat up the air, iron, hot plate, all this is to use heat to sort of like make our lives easier. So there's also those that converts electrical energy to kinetic energy, such as your fan, okay, and many other more. Your lamp is actually converting electrical energy to light energy. So first chapter is just sort of like this first section is just to let you understand that electrical energy has its uses. Okay, it can be converted to different forms to enhance our life. Okay, so that's really the key idea here behind 17.1. As you read it, okay, it's just really a lot more details on to appreciate what electrical energy is used for. Okay, so that's really the whole of section 17.1. Okay, now let's go on to 17.2. Now 17.2, there will be two things that we'll be looking at. First is these two formulas over here. So P equals to VI. That will be the first formula in the pickup. The second one is E equals to VIT. So we'll be looking through it at a later part. And the next one, learn how to calculate the cost of using electrical appliances where the energy unit is this one called kilowatt hour. So kWh actually represents kilowatt hour. Okay, so 17.2 got two main ones. So first up, okay, I just need you to look at this here. So typically power, okay, you have actually covered in chapter 6. Okay, you actually measure power in the units of watt. So 1 watt is equals to 1 joule used per second. Why? Because power is equals to energy over time. So power equals to how much energy is used per second. So this was what we got in chapter 6. So what they did was actually, in chapter 15, you learn these two different formulas. They rearrange it, they substitute it in, and they get this. Now, this whole part here, don't need to memorize, don't need to remember, okay? Don't need to remember how P equals to VI is derived. Okay, I just need you to understand, not that you don't need to remember these formulas. You need to remember them because it's in your current of electricity. What you don't need to know is how you get from P equals to E over T all the way until here. Okay, you don't need to know how the whole thing is derived. Okay, so key idea here, what they're trying to show you is, all the formulas, when you combine them, you actually get P equals to VI. Okay, now, for P equals to VI, do take note. Okay, P is power. Okay, the units is watt. V is voltage. or potential difference, the units is volts. I is your current. Units is ampere. Okay, so volts is V, capital V, ampere is capital A, watts is capital W. So you're going to calculate power, okay, calculate power in watts. Okay, you can take voltage, multiply by current. Now, I need you to understand this is that when you are doing this formula, okay, you're actually calculating the power for the appliance. So typically, you want to find the power of the lamp, okay, I should be using the potential difference across the lamp multiplied by the current across the lamp. Okay, you cannot anyhow use any single voltage or anyhow use any single current you see in the question. Where you must apply the voltage that's across the lamp, you must apply the current that's across the lamp. Okay, so this part here, please take note of it. A common mistake people always make is they just see some voltage, some current, and they just multiply them to get the power. Okay, of course, if you're stuck, you can do that. But in general sense, you should be understanding what voltage, what current you're using. Okay, so this is for P equals to VI. Okay, power equals to voltage times current. Now, this is actually another variant. So other than P equals to V times I, okay, by using V equals to IR or I equals to V over R, you can actually convert the formula to two other forms, okay, which you can see here. So let me zoom it in a little bit. Okay, so P equals to I square R, P equals to V square R is equals to same as P equals to IV. Okay, all these three formulas actually are the same thing. It's used to calculate power. So the question is, when do I use them? Okay, now there's this take note of. So they did say, when are the cases that you can use them. But in general sense, okay, to find power, if I got voltage and current, I'll take P equals to V times I. However, sometimes the question, they give you the resistance. Okay, they give you the resistance, but they do not give you the voltage. Instead, they only give you the current. So if you only got current and resistance, then of course I'll use the second formula. It's the first one, the second one. Now, obviously, from the last one, you can see that if you only got voltage and resistance and you don't have current, then you use the third formula over here to calculate power. So be able to understand how to use these three, be familiar with them. The key idea here is, okay, if you don't have V and I, if you only got one of them, you can either use I square R or V square over R to find power. Okay, so be flexible in the way how you're going to calculate all this. Okay, now, I want you to look at this part of here. Okay, it says the electrical appliances are usually marked to show the amount of power they consume at the operating voltage. Okay, what does operating voltage means? So for example, if a kettle is marked 2000 watts and 240 volts, it means that when the voltage is 240, the kettle will actually convert electrical energy into thermal energy at the rate of 2000 watts. Now, to expand this a little bit, okay, is actually trying to say that it will convert 2000 joules of electrical energy into thermal energy in 1 second. So thermal energy in 1 second. Okay, now some of you are saying, sure, how come watt become 2000 watts and then got 1 second, 2000 joules and then got some 1 second here? Key idea here is what you're trying to say, P equals to E over T. So 2000 watts actually just means 2000 joules of energy is used every 1 second. That's the meaning of 2000 watts. So if something is marked at 500 watts, it means 500 joules of energy is used in every 1 second. Okay, this is also the same as saying 500 watts. Okay, now question. If the thing that we are looking at, okay, is not operating at 240 volts. Okay, so let's say, for example, the electric kettle is marked at 2000 watts, 240 volts, but I plug it in to 120 volt socket. Will it operate at 2000 watt? Answer is no. It will operate at a lower watt or a lower power. So the key here is whenever you see something like this, it means that you need to connect it to a 240 volt supply. Then it will operate to give you 2000 watt power. Okay, so this is the key idea here. Why am I taking some time to go through this? Because if you look through your TYS, there's always the definition question of what does this, okay, what does this thing in the circle means? Okay, so you must be able to explain this a little bit. Okay, you can go and practice it, you can look at the answers in your TYS to really get a better understanding, a better clarity on it. Okay, so I'm purposely highlighting this part so that you're a bit more aware. Okay, typical ratings. So this one don't really need to memorize. Okay, so don't bother wasting your brain space over here. Just need to know that okay, this is just to appreciate it a little bit more. Now, all the worked examples, okay, do take some time to go back and read through after you have had the lecture. Okay, so you have some better understanding of what is this whole thing about. Now, just now what we did was to calculate power. Okay, just now what I did was to calculate power. We know P equals to VI. That was the first formula. Second thing we did was we also know that P can also be equals to I square R. P can also be equals to V square over R. So that's for power. Now, the second part we need to look at is in terms of electrical energy. Because we can calculate power, we can calculate electrical energy. So the formula is actually over here. E equals to VIT. Why is it so? It's really because E equals to PT. Okay, power is VI. So that's why E equals to VIT. Of course, those of you who do not want to try to think too much to derive it, then you can just memorize the formula. So there's another series of three formulas here. Okay, E equals to VIT, I square RT, or V square over RT. What you will realize is, isn't this exactly the same as what we have here, except that it's all multiplied by T? Yes, you're correct. Because the key idea here is E equals to PT, power times time. So can you see power is VI times the T, I can get energy. Power equals to I square R. If I times the T, I'll get energy also. P equals to V square over R. If I times the T, I'll also get energy. And that's why you got this three over here. So from this, you can derive another three formulas, which is E equals to VIT, 2, E equals to I square RT. Okay, I'm purposely writing this out a bit so that it's a repetition for you to remember this. V square over R times T. Now, I need you to take note of this. It is that when we are using this formula, okay, okay, the energy here is in terms of joules. Okay, this is energy. The unit that we are using to calculate this energy is actually in joules. Okay, J. The time here is very specific. Okay, the time here we're actually using in terms of seconds. Okay, so to find energy, we need to multiply by the time. The time must always be in seconds. Okay, if you're ever going to calculate energy in terms of joules. Okay, so please be careful. Here we covered the formula to calculate power. We also derived the formula to calculate electrical energy. So these two more or less settled. Now I want us to look at one example here. Okay, so it says an electrical iron has a heating element of 60 ohm resistance. So this is the resistance over here. It's connected to a 200 volt. Find the electrical power produced in the heating element. So you can see here, I got resistance, I got volts. They want me to find power. That's why I use P equals to V square R. Because I got no current here. I got resistance, I got voltage. So as such, I use V square over R. Calculated, you get 960 watts. Okay, they ask you to calculate the amount of electrical energy consumed when the iron is used for 20 minutes. Now, so if I want to find electrical energy, I use P times T because power is 960. So I use 960 here. Now look at this specifically. 20 minutes times 60 seconds over 1 minute. In general sense, it's just 20 times 9 because you're converting the minutes into seconds. After you have done this, you get this gigantic number, which is 1.15 times 10 to the power 6. Now, can you imagine the electrical energy used, okay, by the iron when it is being used for 20 minutes is this big number. Okay, can you imagine the electrical bills they're gonna have, that you're gonna see is always in such a big number. It's not practical at all. As such, okay, finding energy in terms of joules, okay, we normally use it for science to calculate in terms of energy in terms of joules. Right? E I okay? We use to calculate this energy in joules, we use all this formula. Now, as I mentioned, the number is very big. So in a very pragmatic sense, okay, in a very practical sense, okay, you will definitely not want to see this kind of thing in your electricity bills, or it just scare everybody off. As such, the next segment we're going to look at, is really about how to calculate the way how electricity is calculated in the real world. Okay, so there's another way to calculate electrical energy. Okay, we instead of finding energy in joules, okay, instead of finding energy in joules, sorry, let me erase. Instead of finding energy in joules, okay, this is the one that we typically are calculating in the front. Okay, they have now converted to finding energy in terms of kilowatt hour. Right, kilowatt hour is another unit of energy. Okay, now, so this is the one that they use in the real world because it's a lot easier. One way to remember what is 1 kilowatt hour is to look at this one here. Okay, see this. Obviously, you can see it's kilowatt hour. So to calculate the amount of energy used, so to calculate energy is power times time, right? Typically, the power I use watt. Typically, the time I use seconds. However, if I want the energy, so this for in joules, in joules. In joules, okay, this is the typical ones that we calculate. But I want to calculate energy in kilowatt hour. So what I'm going to do is, same thing, I'll use power times time. But the power now, instead of using watts, I'll use kilowatt. You see kilowatt over here? I'll use kilowatt for the power. For the time here, you can see it's hour. So I will use the time in terms of hours. Okay, so you can see it's gonna, in terms of the units, it's different, although the formula is the same. Okay, so I say again, even though the formula is the same, the units are different because the energy units is different on its own. So let's try a little bit. Okay, let's skip A. Okay, let's skip BR, don't care BR. Oh, so they say a 1.5 kilowatt electric heater heats up water for 2 hours. Calculate the electrical energy consumed by the heater in kilowatt hour. So energy in kilowatt hour is power times time. Because I want it in kilowatt hour, so my power must be in kilowatt, so this is good. The time, I need it to be in hour, so it's good also. Such electrical energy consumed in kilowatt hour is 3.0 kilowatt hour. Imagine if you calculate it in joules, you're gonna get this big number, okay, which is actually 1080000. Okay, it's such a big number here in terms of joules. You realize it's not practical to use this kind of numbers. As such, in practical electricity, you need to learn how to calculate energy in terms of kilowatt hour itself. Okay, so yes, do take note of this. Okay, common mistake that people make. They think that kilowatt hour is actually power. Okay, they thought kilowatt hour for amount of electrical power. No, this is not power. Kilowatt hour is actually the amount of electrical energy consumed. So do take note of this. Okay. Okay, now all this is a bit more examples here. So do take note how to use it. Now, I'd like to highlight one point over here. Okay, in your exam questions, other than calculating electrical energy, okay, in kilowatt hour, sometimes they ask you to find the cost of electricity. Okay, cost of electricity. Now, to find the cost of electricity, I need to take note of this. You need to take the amount of energy used, amount of electrical energy used, multiply by the rate. Now, what is the rate? So, sort of like if you look at this here, 27 cents. Well, this is the rate. Okay, different question, the rates are different. Okay, so just take note of it. So, if so, you just need to take the amount of cents per kilowatt hour multiply by the amount of energy used. You can get the total cost of electricity. Okay, so this formula here, do take note, is not really covered in the learning objectives just now. Okay, but you will use it in your exam questions, in some of the little worksheets that you have to do. Okay, so just take note of this formula over here. Okay. Okay, so we have gone through quite a fair bit in terms of the formulas used. Okay, so we have gone through P equals to IV, P equals to V square R, P equals to I square R. So we learned that electrical power can be expressed in these three different formulas. In terms of electrical energy, okay, E equals to PT can also be equals to VIT. But we also know that it also can be expressed as I square RT. Energy can also be expressed as V square over R times T. So these are all the various formulas for electrical energy that we can use. And the last one, we also learned that kilowatt hour is a unit of electrical usage. How to calculate this? We use E, but the power here we will use kilowatt. The time here we'll use in terms of hours. So that's what we went through in 17.2. Okay, you can do the test yourself. It will really help you to consolidate whatever you picked up for in this summary lecture. Okay, now this first part here, typically in practical electricity, is going to earn you the marks in terms of the calculations. Okay, most people, in terms of calculations, your struggle doesn't really lie in this part here. You will normally struggle with the DC circuits part on how the current split, how the voltage is constant, and whatsoever. Okay, most people, for these calculations, are not so bad. Okay, but the main problem people have is in terms of expressing the answers for the explanation in practical electricity. Okay, so this part here, I will be going through in detail of how to express the answers in terms of the safety features of electricity, and also how to state the hazards itself. Okay, so let's go to 17.3 now. Okay, in 17.3, we just need to know how the use of electricity can be hazardous. So how is it hazardous? Generally, you always got this cable, got this insulation from the wires. So the wires actually carries your current, the electricity to your various components. But across time can be either the rats eat it, or because like your handphone chargers, okay, because you keep twisting the cable, you will see something like this happening. Now, so when you keep twisting it, the insulating material can become worn with time. So the key idea here is when it becomes worn, it exposes the conducting wires. And when the wires are exposed, when people touch it, they can get electric shock. So the key idea here, exposed conducting wires can cause electric shocks. So one of the dangers of electricity is that it can cause electric shocks. Right? One danger is that electricity can cause electric shocks. So if I got worn out wires, these worn out wires could possibly touch the appliances casing. When I touch the casing, I will get the electric shock. Okay, so this is one of the situation here. Okay, second one is that overheated cables can cause fires. So electricity can cause fire. Okay, cause fires due to overheating. Okay, now how does this overheating occurs? Okay, so typically when you overheat extension onto another extension, then plug many things onto that one same plug, then that's it. You're asking for trouble. Why? A large current, okay, causes high heat. Okay, typically, when a lot of current flows through an appliance, as long as current flows through an appliance, typically it will produce heat. Just like a handphone, when you're charging it, you realize the charger gets hot, you realize that your handphone gets hot. Or when you play the game on your phone for very long, okay, your handphone gets hot because a lot of current is flowing within your handphone itself. Current causes heat. Now, when I have a lot of current flowing at a time, you realize that it will cause a lot of heat, and when it becomes that, it may cause a fire. Most of us, our concerns is not so much on number two, because the industries will have done their proper assessment of what kind of wires to use. Okay, so most of the time on our end, problems that we the so-called what causes the hazard is because we overload power sockets. Okay, so please do not overload power sockets at home. You will, and you don't want this in your home, Damn environment. Damn environment just means got water lah, got water around. Hey, got water around. So as you read, key idea here, water in contact with the uninsulated electrical wires providing path for the current. Okay, so generally your electrical appliances are insulated. They are electrical current doesn't flow out from it. But if you got have it in contact with water, the water in contact with it provides a conducting path for the current. So it provides another way that the current can flow. So water actually sort of like behaves a little bit like a wire. So if your electrical appliance touches the water, it's sort of like an extension of the wire. And when you touch the water, the current will flow through the water and flow to you, and that's why you can get electric shock. Now, sometimes because you may draw a lot of current to you also, and hence large current may also start slowing. And when you hear large current, you also think of fires. So it's not only causing shock to you, but because you also will draw extra current, it causes a high flow of current. As such, it can. Yes. Okay, so damp environments not only cause shock, okay, so one thing it can cause electric shock, right? So must remember, key idea here is either overloading to cause a lot of current to flow and hence you got fire, or because current starts to flow through you, it will actually cause electric shock. In hazards of electricity. Okay, I mean two main outcome of what the dangers of electricity are. Okay, damage, insulation. These are the situations that can cause. What do we do at home, or what's happening at the house to prevent us from getting shocks and getting the fires? I'm sorry, but this is really the part where there's quite a fair bit of things you need to remember. Okay, you alright? Describe the function of fuses and circuit breakers. Now, fuses and circuit breakers function quite similarly. Okay, so later on we'll go through them. Okay, we also explain why metal cases should be earthed, and we also learn what is this idea of double insulation. Next, we also learn to define the term of live, neutral, and earth wires. We will learn how to describe the wiring in the main plug. This one quite important. Frequently tested. Okay, the safety mechanisms in place. And lastly, explain how the switch, fuses, and circuit breakers are fitted to the live wire. I explain why these three are. So these are the things we're going through in 17.4. So you can see there's really quite a. don't need to memorize it. Okay, you just need to. It's just so let you know how the home appliance is like. Home electric volts. This negative terminal. Okay, it's like the 0 volts. This is like the neutral wire. Both the live and the neutral wire needs to be present because with the live and the neutral wire, the current can flow through it. Imagine you don't have the neutral wire. Will your light bulb light up? Answer is no, because you realize it is now open circuit. So the neutral wire actually sort of like allows the current to flow back to form a complete circuit or to form a closed circuit. So do take note of this over here. Okay. So live wire is normally the dangerous wire. The neutral wire, because it's at 0 volts, is actually not dangerous. Okay, so if you're home, you see a 3 pin plug there. Okay, you see three holes over there. There's actually a 1/3 chance if you put your finger in, you'll get the shock. Right? When you put a finger in to the live terminal or the live wire is already connected, that's the volt. That's the one where you have to have finger in, you'll get the shock over there. Okay. Some of the safety features can be found in our homes are listed below. So your circuit breakers, we got fuses, we got Hey, sorry, I realize that some of you are telling me that you can't really hear me. My voice keeps getting disconnected. Let me check my speaker settings. Okay, so sorry, thanks for highlighting this. Uh, okay. Uh, Let me change the setting a bit. Okay. I hope it's better now. I think it's getting disconnected here and there, partially because I'm using this function called voice focus. So it's if as long as I'm not within the range, I will get automatically cut off lah. I hope now it's better now. Okay, hopefully the voice is clearer. Okay, so back to these safety features. I got 1 to 6 that I'll be needing to go through. Okay, 1 to 6 are tested in your syllabus, so you need to know all of them. Okay, first thing first, circuit breakers. How do circuit breakers work? Okay, so it's the one that you have at home over here. Okay, so key idea here, the circuit breakers, they switch off the electrical supply in a circuit when the current flow through them is too much. Now, how do they switch off? They actually do this. They disconnect the high voltage terminal. Okay, so I say again, circuit breakers are safety features. They switch off the electrical supply. And how do they switch off the electrical supply? They actually disconnect the high voltage terminal. So back to the typical circuit over here. Okay, so imagine this like the 240 volts, this like the 0 volts. So when too much current is flowing through this wire over here, too much current is flowing through this wire over here. So what the circuit breaker does is it will actually disconnect. Okay, it will actually cause the circuit to cut off. So it will like open up this part here, it will cut off here. So once it cuts off here, okay, current cannot flow to your lamp. As such, it will not damage your appliance. It will not cause too large a current flowing through it. So you won't get shock, you won't get fires. Okay, so that's what the circuit breakers does. Okay, it will disconnect your circuit when the current flowing through it is too large. So example, I want you to look at the numbers over here. Can you see 16 ampere, 16 ampere, 16 ampere, this 16 ampere? So these four terminals here, okay, they actually will allow maximum 16 ampere to flow through. This thing will flip down. Okay, so let me use red color. This thing will flip down, okay, when the current exceeds 16 ampere. So once you got 16.1, this thing will flip down. 17 ampere, obviously, the thing will flip down. Okay, this one here is a 25 ampere. So you can see here, even within the circuit breaker itself, there's different ratings. Okay, now, so this 25 ampere one is actually for the more, for the electrical appliances that requires a little bit more current, such as your air conditioner. Air conditioner is the main one that takes up a lot of electricity actually. But you can also see here, that is a 10 ampere one. Okay, so different circuit breakers, depending on what plugs are connected to which one, okay, actually provides a different cutoff. Okay, some at 16, some at 25, some at 10. Now, the good thing about circuit breaker is when it flips down, that means it cuts off the current from flowing. All you need to do is to just switch it back up, and things will start to run normally again. So circuit breaker is sort of like you can keep getting it switched off, then you can on it again, getting it switched off, you can switch it on again. So it's reusable, right? So key idea, okay? Take note of this part over here. Okay? Okay, which is whatever that I explained over here. So this is just a further elaboration on it. Now, the next one is this thing over here, the fuse. Okay, so you can see here they say the fuse has the same function as a circuit breaker, but a fuse has to be replaced if it blows, whereas a circuit breaker can be reset if it trips. So the difference between a fuse and a circuit breaker is that a fuse must be replaced once it is activated. Okay, once it blows, you must replace the fuse. Whereas for circuit breakers, you can just reset it by switching it back on. Okay, now for a fuse, what are the key things you must understand here? I need you to remember this whole statement here. Typically, a question that I ask is, how does a fuse function? Okay, in the exam question and test, when you go straight to the test, you realize that there was, how does a fuse function? So what you need to write? A fuse consists of a short piece of wire. So you can see this is a short wire. Okay, the wire is made thin. So okay, the wire is thin. So obviously, you know, if you look at all these things here, can I shorten this whole thing here? Yes. So this whole part, you can just write a fuse consists of a short, thin wire. Okay, so you can just combine the whole thing together. So that when a large current flows through it, it becomes heated up and melts. Okay, now imagine when it heated up and melt, you'll break. Okay, so a gap is introduced and the circuit is open. Now, why is it that the current stopped flowing through the circuit? I want you to remember to write this. It is because the high voltage terminal is disconnected from the appliance. Okay, what is this high voltage terminal? As I mentioned just now, it is sort of like the live wire is disconnected away from the appliance itself. So current can't flow into the appliance because you have cut off the high voltage wire. Okay? Okay? So now, so this is the description here. I'm sorry, but you really need to memorize it because most of the people always miss out certain info, such as, you know, large current flow through it, or like or the circuit is open. They miss out all the little words. So do take note of this. Be very specific. Be very meticulous in trying to remember this. Another question that people will think, this one important. Okay, this one important? Answer is yes. So I'm sorry, you need to remember the fuse ratings 1, 2, 3, 5, 10, and 13. Why do I need to remember them? Is because in the question itself, they always like to ask. They ask you to calculate the current flowing through an appliance. Then they ask you what is the fuse rating that you should be using for it. So typically, you need to, for example, if a current that's flowing through, so let's say for example, this lamp, okay, this lamp, I know the current flowing through it is 1.5 ampere. And 1.5 ampere typically flows through it. So what is the rating of the fuse I should be using? Okay, because there's no 1.5 ampere fuse, I'll actually use the next one, which is 2 ampere. Typically, we will use a fuse rating that's slightly higher than the current that's flowing through the appliance. So if 1.5, I'll use 2. If I got 2.8 ampere current that typically flows in the circuit, I'll use a 3 ampere. Okay, so remember this, that the fuse that we use will always be slightly higher than the current that flows through the circuit. Okay, so please take note of this. Okay. Now, okay, what is mentioned here is whatever that I've said. So you can see the fuse should have a rated value that's slightly higher than the current. Okay. Fuse should be connected to the live wire. Do take note of this. The fuse should always be connected to the live wire so that the appliance will be cut off immediately. So the current to the appliance will be cut off immediately. Okay. And it will not be at a potential of 240 volts. This is what I mean by the high voltage terminal. Okay. Next one, please take note, this one is more for the safety feature. Sorry, maybe I shouldn't put a star. This one is really just more for the safety. If any one of you need to replace a fuse, please turn off the main power supply first. Okay, don't kill yourself. Okay, so that's for the fuse. So key idea, we talked about the circuit breaker, we talked about the fuse. Okay, both of them actually cuts off the high voltage terminal when the current flowing through an appliance is beyond the rating. Okay, beyond the rating. So that's for this. Okay, next one, switch. Okay, switch are designed to break or complete the electrical circuit. So open, switch, so we close the circuit or we open the circuit. Now do take note, switch should always be fitted to the live wire of the appliance. Why to the live wire? Okay, so because the idea of your switch is to disconnect or connect the circuit, the appliance to the high voltage terminal. So realize I keep saying this high voltage terminal thing. Why is it so? Is because the live wire, which is the high voltage wire, is the one that carries the current in. So if you want it to be safe, you must have something that can cut off the live wire. So that's why fuse, circuit breaker, cuts off the live wire when your appliance becomes dangerous. Same thing, the switch also cuts off the current from the live wire when the appliance becomes dangerous. So switch is meant, okay, to be fitted to the live wire of the appliance. So you can look through the examples here. Okay, so typically, okay, you can see here, wow, how come the wire touch the casing on? Because of electrical faults. What are examples of this electrical fault that can cause the live wire to touch the metal casing? Is when you got damaged insulation. Damaged insulation. Okay. Now this damaged insulation that is like what you have seen just now, one of the dangers where the cable, the cabling, the insulator actually is worn out, and then the wires are exposed and it touched the casing. Now, so imagine something that has a metal casing over here. Okay, then the fella touches it. So can you see live wire, 240 volts? When I connect to the casing here, this whole casing is 240 volts because the live wire touches it. This man here, when he touches it, okay, just take note, the ground is normally 0 volts. 240 volt over here, 0 volt. Can you see that there is a potential difference? Okay, there's a difference in the voltage. When there is a difference in voltage, when there is a difference in voltage, or when there is a potential difference, okay, comma, current will flow. So 240 volts here, 0 volts because you are touching the ground. The ground will normally take it as a 0 volts. So current will flow through the guy, and hence bzz, you get electric shock. Okay. So what you want to avoid is this kind of situation here, because they say even when the switch is open, but because the live wire is touching the casing, current will still flow through the person. So you realize it's stupid to place a switch on the neutral wire. Or I say here, it is stupid to place a switch at the neutral wire. But of course, I always get a lot of kids drawing the switch at the neutral wire because they do not know where to place it. As such, please remember, if the question ever asks you to draw the switch on the live wire, okay? On the live wire. So you do it on the live wire, you realize I open the switch here. This whole casing is not 240 volts. As long as it's not 240 volts, okay, actually it will become 0 volts. This thing now is now 0 volts. This thing is connected to 0 volts because to the ground. 0 volts, 0 volts. No potential difference. So if there's no potential difference, will the current flow? Answer is no. Okay, so you realize switch always connect to the live wire. Okay, because why? It is to disconnect the live wire. Okay, key idea that I've written here, switch is to this. When you open a switch, opened switch, okay, is to disconnect the appliance from the high voltage terminal. So this is one key phrasing I need you to remember. Okay, so that's for switch. So we have gone through 3 of them. We've gone through the first thing, which is circuit breaker. And we have gone through something that's quite similar to the circuit breaker, known as the fuse, and you need to describe it. The third thing we've talked about is the switch. Now, all these 3 functions in the same way, which is to disconnect the high voltage terminal from the appliance. Okay, how they do it, each of them functions slightly differently. Okay, so just take note of that. Now let's go on to earthing. Okay, so let's go into basics first. Typically your wires, okay, when you have your plug, right, you realize you got a 3-pin plug like this, like this, like this. Alright, so there are actually 3 main heads that come out from it. One of them is actually your earth wire. Okay, earth. The other one is neutral, the other one is live. So live and neutral, I've gone through it. Okay, this is the high voltage one, high voltage live wire. So this is the dangerous one. Okay, the neutral wire is the one that is at 0 volts, so it provides a return path. So this one is actually quite a friendly one. Okay, friendly. I put it in inverted comma, friendly. But please don't use this word. Please don't use this word in exam. The last one is the earth wire. Okay, the earth wire is a low resistance wire that's usually connected to the metal casing. I want you to circle usually connected to the metal casing. Okay, because the earth wire is not connected to the live wire, the earth wire is not connected to the neutral wire. It's actually a separate wire that connects to the metal casing and then to the ground. So if you go down, okay, you look at this here. Not this one, sorry. Look at this here. It's a little bit weird. Okay, it's a bit weird. If I could redraw this, okay, it's actually this whole washing machine. Okay, there's this wire that touches the washing machine that goes to the ground. Okay, this wire that touches the washing machine and goes to the ground is called your earth wire. Okay, typically how the current will flow, okay, it is from the live wire, it flows to the motor. From the motor, it flows out through the neutral wire. Okay, this is the typical flow of how the current is going through. Okay, you realize it doesn't go through the earth wire at all. Okay, now, But what happens is that when there's a fault, okay, due to electrical fault, due to the live wire touching the metal casing, once again, damaged insulation is the one that causes it. So if there is a damaged insulation, which means that this whole washing machine is now 240 volts. So if you touch the washing machine, generally the current will flow through you. But because there's this earth wire now, so do take note, the earth wire actually causes the current to flow to the ground through itself. Why? Because the earth wire is a much lower resistance wire than the person. So if I go back here, go back, you realize, what did they say in the description over here? The earth wire is a low resistance wire. It's very important to write this down. Okay, whenever you need to answer exam questions, they ask you what's the earth wire. You must say that the earth wire is a low resistance wire. It's usually connected to the metal casing. So in general fact, if I have to erase all this whole thing is very important whenever you need to describe earthing or earth wire. Okay, so because it has low resistance, it's connected to the metal casing. If there is a fault, the earth wire actually causes the current to flow through it instead of the person. So the person don't get electric shock. But what happens next when the current flows through it? It draws the current away from the person. Okay, the person doesn't get a shock. But on the other hand, because of the way how the earth wire is drawing the current away, it actually creates a short circuit. What's a short circuit? A short circuit is like a low resistance path that causes a lot of current to flow through. Now, in your mind thinking, sure, a lot of current. So the fuse and the circuit breaker will activate, is it? Answer is yes. So because there's a sudden surge of current, or a very large current starts to flow through, this exceeds the fuse rating. It either causes the fuse to blow and hence open the circuit, or the other way is the circuit breaker will trip. Okay, the circuit breaker will trip, and all this will actually cause the electrical supply to be cut off. This sentence here typically will write disconnect the high voltage terminal. Okay, high voltage, disconnect the high voltage terminal. So for earth wire, what you need to explain is earth wire is a low resistance wire. So let's worry up. Okay, typically when they ask you describe or explain what earthing is, you will always first write this part here. Low resistance wire connected to the metal casing. How does it function? What you're going to say is when there's an electrical fault in the appliance where the live wire touches the metal casing, okay, the earth wire allows the current to flow to the ground because it has a much lower resistance. This prevents the person from getting the electric shock. So other than preventing the person from getting electric shock, you have to say the earth wire also causes a short circuit, and this causes the fuse to blow. So there's quite a fair bit of things to write whenever you are writing on earth wire itself, because the whole sequence of event, it has quite a fair bit. So do take note of it. You must describe the earth wire. You must describe the flow of events that happen and what the earth wire eventually does in the sequence of event. Okay, so that's for earth wire, the earthing itself. Next one, 3-pin plug. 3-pin plug, the key idea here is still the earth wire. So actually not so much issue. Main thing you need to know is where the wire should be connected. So the earth wire is a green and yellow wire, so it's normally connected to the top here. So this top wire, this top pin over here is normally the earth wire. Now, by looking here, actually you wouldn't know which is the earth, which is the live, which is the neutral. You must look at the whole setup from the back. Do take note, the live wire is typically brown and it is connected to the fuse. Okay, so I say again, typically the live wire is connected to the fuse. Okay, so it's a brown wire that's connected to the fuse. This is the fuse. Okay, the neutral wire is connected to the terminal, to another terminal. Okay, so you can see at the top here, that one confirm earth wire. Whether this or this should be the live or the neutral, find the fuse. The live wire should always be connected to the fuse. Okay, so this one they like to test. You need to know how the connection is supposed to be. So if you do your TYS, you realize quite a fair bit of this will come out. It's actually a giveaway. You must take note of it. Now, another typical question that they like to ask is this. Okay, so in a circuit like this, then they'll say, okay, live wire. Oh, sorry, let me. It's not drawing now. Seems like the thing is a bit off. Can I draw here? Nope, they're not letting me draw. Why? Did I draw too many things already? Okay, let me save the file a bit first. Oh no, it's not drawing. Okay, never mind. Somehow it's not working. I still don't know why. Oh yay, can already. Okay, good. Okay, now one question that likes to be asked is this. Okay, it's actually like this. So they say that, okay, I got a live wire, I got a neutral wire, I got the earth wire. Okay, then they ask you, what is the current that's flowing through each of these? Okay, first thing they'll tell you, okay, the live wire has a 3.5 ampere flowing through it. Then they ask you complete this. Okay, tell me what's the current flowing through the neutral wire. That's the first part. Find for me what is the current that's flowing through the earth wire. How would you know what's the current flowing through it? Okay, think in terms of a light bulb. Okay, remember I told you this wire here is like the live wire. This wire here is like the neutral wire. So if 3.5 ampere flows through here, how much current is flowing through the neutral wire? So remember, current flows like this, 3.5, 3.5, 3.5, flows through the appliance, and then it goes back to neutral. So this amount, so the current actually flowing through here is also 3.5 ampere. So for the neutral wire, it should always have the same current as the live wire. Now, how about the earth wire? When an appliance is working properly, remember the earth wire is connected to the metal casing. It's not connected to the main circuit. Does the metal casing normally have any current flowing through it? The answer is no. As such, in a typical setting, your earth wire should always have 0 ampere. So I say again, the live and the neutral should always have the same amount of current flowing through it because it's like a closed circuit. The earth wire, because it's connected to the metal casing, is a safety feature. It's not connected to your main circuit. Okay? As such, the earth wire should always be 0 ampere when the circuit is operating properly. Okay, this is very common coming out in the papers nowadays. So please be able to decipher all this. Okay, next one, double insulation. Okay, so first things first, what is double insulation? Is this interesting symbol over here. So it looks like a square and having another square inside it. So this is the symbol for double insulation. Now, how do you know which household appliances have double insulation? First, look out for this sign over here. Look out for this thing. This thing tells you double insulation. Now, other than this thing telling you it's double insulation, what they also mention is that 2-pin plug appliances actually uses double insulation. So what exactly is double insulation? Take note, double insulation is not equals to 2-pin plug. Okay, I say again, double insulation is not equals to 2-pin plug. Okay, so what exactly is double insulation? So do take note, double insulation, from the word double insulation, it means that there's 2 levels of insulation. What are the 2 levels? First, the electrical cables are insulated from the internal components. So for example, okay, these are my wires. Okay, the wires obviously are connected to the internal components. So for example, the wires in the fan, okay, it has a layer of insulation that protects the wires from the other components. So every single electrical cable is insulated from the internal components. Okay, so I say again, every single one of these wires are insulated from the internal components. Okay, so the wires are insulated from the motor, can be from the whatever other things that you have inside the electrical appliance. Okay, so this is the first layer of insulation, or the first level. Sorry, let's be consistent. First level of insulation. Now, what's the second insulation here? So the internal components are insulated from the external casing. So typically, okay, you look at all these casing here, you realize whenever you got double insulated appliances, the casing is also normally plastic. Okay, your casing is also normally plastic. The internal components also, you will see some plastic wrapping and stuff like this, or plastic around it. So that's why you also realize the internal components are insulated from the external casing. So you realize two levels of insulation. Cable, insulated from the internal components. Cable, insulated from the internal components. Next thing, the internal component insulated from the external casing. So you can see here, insulated once, insulated twice. That's why this is called double insulation. Okay, and because it's double insulate, there's double insulation, I won't need an earth wire because my casing is normally also not a metal casing. Okay, that's why typically it is two-pin plug, because casing is made of plastic. So do take note of this for double insulation itself. Okay. So what we have gone through, so we did say that circuit breaker prevent excessive current. Okay. This detects small leakage current to the earth. You can go and read out a little bit more, but we didn't really go through this because obviously I didn't go through because it's out of control. Next one, fuse prevents excessive current flowing through the appliance. Okay, it's always connected to the earth, to the live wire. So you can see these two, circuit breaker and fuse, very there is something in common there. Okay, the next one should be switch. Okay, I don't know why they put the earth wire up front first. The next one should be switch. Switch is always connected to the live wire of appliances. Okay, switch is always connected to the live wire of appliances. And this satu, dua, tiga, this connects. You realize I keep emphasizing this because people always tend to miss out on this. This connects the high voltage terminal. Or some of you would like to say, disconnect the live wire from the appliance. Okay, so A, circuit breaker, B, fuse and switch functions in the same way. Earth wire is slightly different. We have gone through that. It's actually connected to the metal casing. It is a low resistance wire. So it provides an alternative conducting path for the current to flow to the earth when the metal case becomes live. Live actually just means that when the metal case is of high voltage. So you realize the words that you use are quite interchangeable. Sometimes when you don't understand what they mean, you get very confused easily because like, why sometimes they put live, they say it's 240 volts. Do take note, it's just the same thing. Okay, next one. 3-pin plugs, we went through it. Key idea here, you need to know what's the color of each cable, the color of the cables. Okay, you need to know the positions of the wires. Okay, so that's the key ideas here. And last one is about double insulation. Okay, it removes the need for the earth wire. That's why it's normally 2-pin plugged. Okay, but as I mentioned, double insulation does not equal 2-pin plug. It just tells you that I have the wire insulated from the internal components insulated from the casing. Okay, so that's it for this. Okay, so within 1 hour, managed to cover the chapter 17. All those I've said, fill it up in your summary notes. Key idea, go and practice after this. Okay, because it's about getting used to the phrasing, getting used to understanding what the question is asking you for. It is not a difficult chapter, it's actually relatively easy, but most people's concern is that it's normally fused in together, okay, it's normally connected together with the chapter of DC circuits. So it becomes like calculation looks so difficult, even the explanation, because you're so bogged down by the calculation, you're stuck also. So go and practice on your own. If you've got any questions, please feel free to ask your teachers. Okay, so I'm still on reservist, so I won't be around for the next 2 weeks. So those from my class, please go and ask your relief teacher lah. Okay, of course you can text me lah, but up to you lah, up to you. Okay, so that's all from me. Nothing else ready. I will end the session. If you got any questions, okay, I'm gonna stop recording. You can ask me after this lah. Okay, so stay online. Yes. So that's all from me.